All right. So thank you for inviting me. Nice to meet Harry as well, albeit virtually. Today I'm going to talk about something called a technique called theory exploration. And it's all about trying to formulate new and interesting conjectures. So this is a key skill in mathematical reasoning, but it's also very hard. And I can also say that I came to work at this. The reason why I maybe know many of you in the room is that I used to do a PhD in Scotland at Edinburgh Uni with Alan Bundy many years ago. And then I worked on automating proofs by induction. And there it's often the case that you might need some auxiliary lemma for your proof to go through. And this was a technique which we started to develop back then. So theory exploration is not exactly a deduction problem. You're not just reasoning towards something. It's not really a machine learning problem either, but you're trying to kind of find out properties about the functions and the data types and concepts that you have at hand. And the theory exploration system should suggest to you some interesting conjectures about this. So today I will focus mostly on how we synthesize these conjectures. And I'm going to talk about a system called QuickSpec, which is under development at Chalmers. We have built several other tools around QuickSpec, but this is really the core of it, which deals with inventing these interesting conjectures. And then towards the end, I will mention a little bit about proving those conjectures, but we'll start with inventing them. Now it doesn't want to change slides. There we go. So a little comic as an overview of this talk. So there's this little user saying, hey, I heard about this weird kind of numbers that are called octonions. So these happen to be the lesser known of the four normed division algebras that we all know and love. The other being the real number, the complex numbers, and the quaternions. So the user says to QuickSpec, can you tell me something interesting about these octonions? Sure, says QuickSpec. And a second later, it spits out a long list of equational laws. And the user says, well, this looks really interesting. Turns out that octonion multiplication isn't associative. Ah, cool. And property number 13, I recognize as something called the Mufang identity. Ah, so these octonions form something called a Mufang loop under multiplication. So this is from an experiment that I did with Nick Smallbone. We wanted to take some piece of algebra that we didn't really know and give it to QuickSpec and see if we could find properties that have been given names by mathematicians. And it turns out that it spat out 12 out of these 14 properties actually do have names in algebra and were sensible. So we were quite happy with that. Okay, so how did QuickSpec do this? So QuickSpec starts building terms. And by terms, I mean the thing that's on the left-hand side or the right-hand side of these equations. So it starts building terms like that, starting from the small ones. And then it generates random values for these variables, x's and y's. And then it simply sees which ones are equal. And it tests this on many, many values. So it needs something called a generator function for each type. So those of you who are familiar with functional programming, you might know about quick check for Haskell, which is what we use to generate these random values. So then the user asks, well, really, how does this scale? And QuickSpec says, yeah, well, I do have some heuristics as well. So one of the important heuristics that we use is that we always start with the small terms. So you can see in the list there that the small equations come out first. And that's good because there are simply fewer of the small terms. So it's a good place to start. And also it never generates any terms that can be reduced by an equation that it already knows. So you don't get a lot of redundant ones. So it's got to do this, it's got a little rewriting system built into it, which is actually quite a good rewriting theorem prover by itself. It's called the TWI, and it's won prizes in the CASC competition at the CADE conference. So far, we've not done anything about proofs, but you can hook QuickSpec up with several theorem provers. So for instance, we built systems around this where you prove in Isbell-Hall, use automated provers such as E, C3, and so on. And towards the end of the talk, I will also say a little bit more about what we plan to do. So can we learn what sort of conjectures are found nice by humans and tackle even bigger theories? So this is quite a small examples of the octonions. It's just got a couple of functions. But yeah, I think it's quite nice illustrative examples. You take this kind of weird bit of advanced algebra and it can spit out some sensible equations. Anyway, let me go into talking a little bit more about how QuickSpec works internally. So I've alluded to this already, but we're going to look at it in a little bit more detail to give you a general idea at least. So QuickSpec takes essentially a Haskell program as input together with a signature, and a signature just specifies what functions that we're interested in. So what's described here on the slide is kind of the QuickSpec loop. So you start on a small term size, and then you're going to repeat these 3 steps until you reach a max limit, which has been specified by the user. So here we're going to pretend that we have already generated a couple of terms. Those are the ones you can see to the bottom left. And now we're going to start testing and evaluating these to create equivalence classes. That's our step 2. So here we're pretending that we're interested in some functions about lists and reversing lists and sorting lists and appending lists together. So that's the plus, that's Haskell notation for append, which I used in this example. So what we do is that we generate some random values. So here in this example, we have 2 variables, x's and y's. And for this step, we're going to pretend that they're simply shared between all of these terms. So we generate one random value for x's, say the list containing 2, 1, and one for y's, say the empty list. And then we plug them into these terms and in place of the variables. And then we evaluate the terms to see what we get. And what we found there is that the first 2 terms, they evaluate to the list 2, 1, whereas the other 3 evaluate to the list 1, 2. So what we find out then is that we can simply cut this pile of terms into 2 equivalence classes, because we know that the first 2 will never magically become equal to any of the later ones for all x's and y's. So you can also assume that these are universally quantified variables. Okay, does that make sense? Good. Yeah. So now, of course, we need to repeat this many times. So we pick a new random value for x's and y's. So this time x's become the list 2, 1, 3, y's become the list 3. And we plug them in again in our terms, we evaluate them. And this time we can slice off the bottom term there. It evaluates to something different than the others. So we slice them off, and now we have 3 equivalence classes. So then you imagine that you have many more terms, of course, and you keep repeating this, adding more terms, figuring out which equivalence class they should go into, and so on. And after many iterations, say 50 or 100, these equivalence classes will stabilize, and you will not get any more slicing off of new terms. And then you move to extract equations. An equation is simply then you take the terms in the equivalence class. So in this simple example, there's only 2, and you put an equal sign between them, and that's going to be your equational conjecture. So in this case, we can extract the reverse x's equals x's, and sort of reverse x's equals sort of x's. Another important step here is that now we can also reduce the search space of potential terms that we need to look at. So for instance, QuickSpec will never go and look at reverse empty list equals empty list. That's true. So we could have that as an equation, but we decided it's not interesting because we already found a more general version. And similarly with these other 2 that are crossed out. So you try not to generate some more complicated version or something that could be simplified into something that you already know. So they are subsumed. And then without this, you would just have an explosion of the search space straight away. So this is quite crucial. Of course, there are more details to this. So I recommend reading the QuickSpec paper if you want to understand the details here. I've simplified a little bit, but at least this is kind of the general idea. This generation of terms rather than equations at the whole equations, and then these testing and evaluating and dividing into equivalence classes. That's really the core of QuickSpec. So now, how about integrating theorem provers? So far I've kind of spoken about this top part of this picture. So you can see QuickSpec there at the top. It takes in a Haskell program and spits out a candidate specification, essentially, as equations. It uses QuickSpec, which is this automated testing framework to generate these example values, as you saw. What we also want to do, of course, is proving these conjectures, or using them as lemmas in a theorem prover, for instance. And for that, we have kind of developed a little middle layer there, which is called tip, which is essentially a format which is very similar to SMT-lib, although we have some small extensions also. But we can express our definitions and our conjectures as tip. And then from tip, we have various tools to translate to, for instance, Isabelle, and also to TPTP and to conventional SMT-lib if we want to pass it on to some additional provers. So this is quite a nice architecture, we think, rather than trying to implement theory exploration directly in some particular theorem prover. We've opted for doing this so that we can combine it with whatever theorem prover we feel like. Right. So I'm going to do a little demo. So this is kind of, maybe some of you have seen this demo before. It's my favorite one, is to get, this is Isabelle. So this is a system called Hipster, which is essentially QuickSpec, what you just saw, hooked up with some automated proofs by induction in Isabelle. So this is actually a homework assignment that I was given at Edinburgh as in my functional programming course. I think they asked us to prove that insertion sort produced a sorted list. And here it's just the definitions of sorted, insert, and insertion sort in Isabelle on lists of natural numbers. And we are going to ask Isabelle to prove this theorem, homework theorem, that insertion sort produces a sorted list. So what would you do then? Well, you would first use Sledgehammer. So I don't know how many are familiar with Sledgehammer, but essentially Sledgehammer is this power tool for Isabelle. Isabelle is an interactive theorem prover, but you can use Sledgehammer to call out to various automated tools such as CVC4, which is like the champion SMT solver out there, or Vampire, champion first order theorem prover. But in this case, Sledgehammer will not give you any help. These will time out. So what I'm going to show you, I think this is a video. I'll see if I can get it to play. So now, instead of using Sledgehammer, I'm going to call our tool Hipster. And I'm going to tell it that I'm interested in sorted, insert, and insertion sort. And it should go off and call QuickSpec and find some lemmas for me. See if that helps with my homework. So now it's done that. It thinks about some proofs. So now it's trying to prove also the output from QuickSpec. And it takes about 3 minutes. So I've slightly cheated here. But here we go. So let's see what's come out of Hipster. You get the output there at the bottom. Oh, it's a lot of stuff. You can click on it and paste it into your Isabelle script and see what happened now with Sledgehammer. Oh, it found a proof. So it says, oh, do simplification and add something called lemma AD. And that's something that Hipster discovered. And that looks very much similar. It actually discovered our homework assignment. And how did it prove it? Well, it did induction, some simplification, and it used the lemma AB. Lemma AB is actually the key lemma that you need for proving our homework assignment. If you have a sorted list and you insert into it, it's still sorted. And that was also proved by induction automatically. And Hipster produced this little proof script. It's not the prettiest proof script. It's just written in this apply style, apply this tactic, apply the next tactic, and so on. But yeah, that's it. So basically what this tool can do is that it can both invent a bunch of lemmas. These are these lemmas with funny names that you can see, lemma A, B, A, C, and so on. It can insert them into the proof script and then use them to prove a bunch of other things. So we're kind of automatically giving Theorem Prover more facts to work with. So that's quite nice. I'll be happy to take questions, by the way. So this talk is not super long. So if you want to ask me something, please do. Recently, Vampire actually got some support for induction. So I thought, okay, well, I'm going to try it and see how it does on some hard benchmarks for induction. So there's this 50 problems from Andrew Ireland and Alan Bundy, which are quite hard for inductive theorem provers because most of them need some auxiliary lemmas or they need generalizations and so on. They're mostly about different data types such as lists and trees and so on. So usually you probably need some sort of tool to find these lemmas for you. So I first tried these, just giving them to Vampire, and it could prove 7 of them at least. So it was, yeah, that's okay, 7 out of 50. But what would happen if I passed these problems first through QuickSpec to do essentially what you saw in this little video, generate extra conjecture, try to prove those conjectures in Vampire, and then try not another time around these benchmarks problems. So then it proved 25, which was another 18. So that was pretty good without really, and I didn't really, I wrote a 90-line shell script to do this. So for a very small effort, you could get quite a lot of more inductive proofs in Vampire. And I should say that Vampire wasn't really, induction in Vampire wasn't really designed to deal with data types. It was, I think they were focusing on proofs by induction over the integers. So anyway, this is kind of a small exercise, but it shows that it's quite easy to couple on new provers to QuickSpec. So basically what you do is that you use these, I mentioned this tip layer. So we have some tools. So this, I'm trying to see, I don't know if you can see my pointer, but you can have a problem expressed in this tip language. So this looks very similar to SMTlib, as I said. And you can pass problems in this format to QuickSpec via a tool called TipSpec, of course. Yeah.
No, that was just me blowing my nose. Sorry, Brian.
Okay. I thought someone was asking a question. It's always a bit funny when you give Zoom talks. You don't know if the audience are with you or not. Anyway, we can give this problem description via a tool called TipSpec to QuickSpec. QuickSpec spits out a bunch of conjectures. So in this case, this example comes from these 50 benchmarks by Ireland and Bundy. So QuickSpec will spit out quite a lot of conjectures. This is about some doubling function and plus and successor and so on. But anyway, we can take these conjectures, feed them into any automated prover that we want. That speaks SMTlib, for instance, Vampire does. And if it proves it, we just add that lemma to our original problem. And then we can retry and see if we get, if we can prove the original conjecture with this extended file. So it's exactly the same principle as you saw in Isabel. You can also do for other provers. And it's quite straightforward. And if you don't manage to prove it well, then you can put it back, see if you can prove some other lemmas, and then come back to it later on. And if not, you leave it open and the user can look at it and see if it's interesting or not. So I think I also promised that I was going to say something about other ways of doing theory exploration. So of course, now in AI, machine learning has been very successful in many areas, and can it do automated conjecturing? I mean, after all, you can do text generation, you can generate computer code and so on. So there has been some attempts there. So for instance, there's some work by Joseph Urban and others on using GPT-2 on the MISAR library. And they managed to generate some novel conjectures. But one of the problems that they have is that they also get duplicates from the library, and you get non-theorems. So basically you get loads of things that look like lemmas, look like theorems. The problem is that a lot of non-theorems, they might look like theorems, it's just that they have a counterexample, but they're not substantially different from theorems. There's also been work by Marcus Rabe from last year on using a self-supervised language model to automatically invent conjectures. And they generate many conjectures, but only somewhere between 13 to 30% were actually new. So they got also a lot of duplicates, a lot of alpha renamings, and some non-theorems. Why is this so hard for sort of pure machine learning systems? Maybe it will be solved soon, who knows? But I think it's because fundamentally we're interested in generating things that are not in the training data. We're interested maybe in a new definition or new things that are different from what you have seen before. So, I mean, language models, they generate things that look like text. And if it, for instance, if it's natural language and it looks like text, it probably sort of makes sense. But here you can generate something that looks like a theorem, but it doesn't necessarily mean it's a theorem. So just repeating learned patterns kind of only gets us so far. You get a lot of rubbish as well. So in general, machine learning is very good on tasks where humans use some sort of intuition, like sensory inputs, vision, and so on, or using a language in which you're fluent, you know the grammar rules without having to think about it. But it's more difficult when you start having some task where you have to resort to some sort of slower thinking and so on. So one interesting aspect is then, are there parts of inventing mathematical lemmas which are intuitive? Because after all, I can look at the output from my system, from QuickSpec, and say, okay, well, these ones are interesting. Oh, that one is really ugly. That happens quite often. That one is ugly. We don't like it. So there is something quite intuitive in what sort of properties that we think are potentially interesting. So let me say a little bit about some ongoing and future work where we started to think a little bit about these aspects. So this is work by my PhD student Solrun Halla Einarsdottir. Yes, as I said, humans are quite good at quickly identify, at least reasonably trained humans, can identify an ugly or a nice conjecture. So I hope many of you will agree that the green conjecture here, it's quite nice. It says that the map function distributes over a pen, for instance. Whereas the second function, it's the second equation, it's quite messy and it's not really clear why that would be interesting. And there is some terms in there like successor of zero, take one from a list and then mapping, and it seems somehow a bit contrived. So if I'm just running QuickSpec on, say, a large list library, I will not only get things like the green one, but also things like the red one. And you start getting these kind of problems, as you saw, that the language models also had you overgenerate, and you generate a lot of kind of weird ones. So it's not only those that run into these problems. But can we exploit this? Can we extract some common shapes and conjectures? So Solrun has started building an extension of QuickSpec, which uses templates. For instance, these could come from things like type class laws, such as distributivity, list homomorphisms, and so on. So these are just 2 examples that I put there. So these are some sort of higher order terms where with question marks F's and question mark G's are holes to be filled in by some functions. So Solrun has implemented an extension called roughspec, which is supposed to take some shortcuts in the search and just search for equations that match these templates. Oops. What happened now? Sorry about that. So the idea there is that templates, they restrict the search space. They say you're only allowed to search for equations that fit this shape. Now this isn't, if you're looking for small terms, you might as well use QuickSpec as normal. We did some experiments with this, and it's usually as fast. However, if you're going to look at larger term sizes, so say terms that are over size 9 roughly, or larger signatures, so say you want to look at the entire list library in Haskell, so that's over 30 functions, then at some point you might want to shift to doing it by this template variant. So she did some experiments and showed that we can, so if we give the entire list library to normal QuickSpec, it will go on for a while, but eventually the search space will explode and it will run out of memory. But using a combination of these 2 techniques, we can also deal with much larger libraries. Yeah. So this was published last year at the IFL conference. And there's a paper if you are interested in reading more about it. Some interesting aspects that we're currently working on is which of these templates should we use and where? So currently these are user provided. So we have a list of common templates, which are just common shapes, distributivity, associativity, and so on, that we think are commonly used. But of course, it depends a bit on what functions do we have. Which reminds me of some work that me and Katja and Jonathan Harris and I think it was June McLean, did many years ago, where this was a bit different, but there we had we were trying to prove some particular conjecture, and we used some machine learning techniques for finding other similar conjectures that had a similar shape. And from those proofs, we were then extract kind of templates from the lemmas that had been used, and then we can find a lemma also for our proof at hand. So one could certainly do something like this. So in the case I've talked about, we're just trying to explore a theory. So we don't have any particular things to guide us, that's any particular goals to be proved. But maybe one could look at things like how is a function, are there similarities between recursive functions? Do they have similar recursive behavior, for instance? That would suggest certain templates should be used. So this is something that we would be interested in looking at in the future. Right. I think I've come to the end of my talk, so I don't know if I've spoken very fast, but we'll at least have time for questions and explanations. And I'll leave you with a slide with some reading if anyone is interested in knowing more. Thank you.
Okay, questions. So my first one is, what is the false positive rate in terms of the things that QuickSpec generates that aren't actually theorems for reasonable, reasonably large? I mean, if you have, 10, 20 function signatures.
So I think for the kind of functional programming examples that I've shown here, there's very rarely any non-theorems among them. I mean, it depends.
I guess it depends on your generating function.
It depends on your generating function, yeah. But I mean, for the sort of normal functional program style stuff, then it's quite good. We have tried it on like co-recursive and co-inductive definitions as well, and there you have to have a slightly different generator, and when you're comparing them for equality, because you have to use observational equality, and then occasionally it gets a little bit worse and something slips through. But I mean, I think it's okay. It's really many more for the experiments we have done in our previous work. We usually find many more things that are actually true. So there's the odd one here and there possibly, but that's okay. I mean, we're aware of that, and you can hook it up with a theorem prover at the other end as a sanity check if you want. Yep,
makes sense. Yeah. My other main question was that is it possible to use it to prove higher order properties? So for instance, if you had the definition of some sort of algebraic structure, a semi-ring, and you wanted to prove some semi-ring, arbitrary semi-ring, lemmas results about arbitrary semi-rings. Would it be possible to use it to first generate semi-ring structures? You'd first have to generate a semi-ring structure, right? A candidate semi-ring structure, and used it to check the debate the semi-ring laws, and then you'd then have to do a second layer of QuickSpec to then work out which derived laws. Maybe I'm not being very clear. Is it possible to do these higher order? I mean, I'm thinking from a dependently typed setting where you're where you want relationships between the proof terms themselves, not just the functions that are being used to generate.
So I'm not sure if I understand your question.
No, I'm not quite sure. That's fine, because I'm not quite sure what my question is. So,
but I think what if I'm guessing what you're on about, I think what you need for QuickSpec is that you need to have some concrete type for which you can generate these ground values.
Yeah.
So, however, you can, so you have to run it on some specific semi-ring, because you have to be able to do the testing where we evaluated terms on values to do this division into equivalence classes. But of course, you can then lift it and sort of abstract it again, which we have done. So you might, for instance, try and prove something for an alpha list, but internally in QuickSpec it discovers it for integer lists, for instance. So we have a few things like that to deal with polymorph.
Okay, yeah, that's the perfect explanation, because it clarified exactly what I was trying to ask in my head. can you use QuickSpec in the generator function for QuickSpec itself in order to generate semi-ring structure? You say that you have to have a concrete semi-ring structure.
Yeah.
You need to be able to use that to generate terms in it.
Yeah. So you have to tell QuickSpec which concrete semi-ring you want to use.
Okay.
I think, well, I should say also that I think there is a variant that was presented not by us, by some other people, that they developed a theory exploration system, which was very much inspired by QuickSpec, but they used symbolic evaluation instead of like we do like concrete evaluation on actual value, but they did some symbolic evaluation. So perhaps that would be beneficial if you were working on more abstract data structures.
So, are you familiar with the Speculate library? That may have been what you're talking about. So there's a recent library called Speculate, which essentially has the same goal as QuickSpec. Have you come across Speculate?
Yes, I think so. That's for Haskell as well, right?
Yes.
Yes. Yes, I believe, yes, let me think. I'm not sure if this is what, if that system was called Speculate, but it isn't Speculate by some people in the UK.
At York.
At York, yeah. Yes, so yeah. So now I wasn't talking about Speculate, but I mean that's another alternative system. So this was by some people in Israel, and now of course I can't remember their names just because I'm in a talk. But yeah, if you go on CAV 2021, you will find their paper. But also I think Speculate does something similar. But it's a while since I read about Speculate, so I might have forgotten some of the details, I'm afraid.
So I have a question. I actually have a few, but one that's about like I guess when you're generating, like when you're using QuickSpec, you're generating test cases, but in some sense you want the test cases, it's like a verification thing. So you want to know that your sorting function, like in your first example, your sort, your reverse, and your concatenate functions, like you're presupposing that they're already defined correctly for QuickSpec to work in some sense, right? Because
yes and no. So I have another demo that I do sometimes where I have a buggy function, and what happens if you have a buggy function is that, well, it will still spit out equation, but just not the ones that you would expect. So when you start looking at those equations, you might get properties that don't really agree with your conception of what this function should do. So you can indeed use QuickSpec as some sort of way of checking your own intuition as to what the program should do and see if QuickSpec's output agrees with that. Otherwise, you probably have something wrong in your program.
And then a follow-up, or maybe for a different part of the talk, but like when you're generating interesting properties about programs, I guess, like how much work does it take for the human? It generates, 100 properties, and you have to go through, and most of them are either hard to decipher because the syntax is bad, or like, is the work that you save by generating them more than it would take to like just think of them yourselves in some sense, because you have to like,
I don't think they are necessarily hard to understand. So I mean, if you remember the little comic that I showed in the beginning, it was a kind of handsome little list of 14 equations, which it generated in 1 second. So yeah. I think in those cases, it certainly saves you a lot of time, because it would probably have taken you more than 1 second to think them up, and whatever, 5 minutes to write a QuickSpec signature. So, yes, I would say it's worth it. Of course, I'm biased, so it depends on what you want to use it for. In your particular case, maybe not, but you should try it at least. It's open source and it's quite easy to install as a Haskell library.
And a question from James, I think, in the back.
Yeah, so obviously everything that you demonstrated so far is focused around equations as conjectures and equivalence class partitioning as a way of giving rise to equations. Have you thought about extending the design of QuickSpec to consider other kinds of properties that are induced by the functions and data types in a given problem domain?
Yeah, sure. So we have done some experiments with also doing implications. And we can do some implications, usually through some kind of trick with expressing it as a predicate, so that you can kind of do the same thing as we do with equations, but then pull out the...
Right. I mean, Philip commented that you obviously do it for sorted, but sorted is given a functional implementation as equations into bool. So somehow it's not, as it were, first class as a property. It's just just another function that you're testing. So.
Yeah. Well, I mean, the tricky thing when you start doing other structures is efficiency. I mean, you can.
Yeah.
It's really this. What makes QuickSpec tractable is this trick with equivalence classes. So yeah, you can do it for other shapes of conjectures as well, of course, but it's typically the search space is bigger, so you can't get as any.
Maybe I will question as well more. So when the use case for QuickSpec is for the user to give two functions, for example, any number n functions from which these equations should be generated, do you find it maybe too restrictive? So because the proofs are hierarchical, right? So suppose I have function f, and then it's used in function f1, and then it's used in f2, and then it's used in f3, and suppose I stopped at f4. And I have the same hierarchy of functions g1, g2, g3, g5, depending on each other. And then I give to QuickSpec that I want to use function g4 and f5 only. But as a matter of fact, an interesting equation would be if I somehow also combine the functions that were used in this chain, not just the top level or bottom level, if you want to call that. Did you think about this problem? Because the examples you give are quite flat. Nothing is depending on each other. And I can imagine it works perfectly if you observe small functions like sort and is sorted. But what if it's a deep hierarchical proof where one function depends on each other, but you want to provide some shallow to explore?
Yeah, sure. So there is some support in QuickSpec for sort of saying that different functions have different priorities. So you can have something called background functions. And I think that's what your functions, that the other functions are defined in terms of would be. So you're not really interested in properties about those functions per se, but rather how they relate. So those functions might occur in properties about the later functions of interest. So then you can give them to QuickSpec as background properties, in which case it will use them, but it will not find the properties about those.
So you can give the ones that you want to use in generation of equations, but you can also provide additional set of functions that
Yes.
would be the background.
Yes, exactly.
So one thing that comes to my mind, if there's no one else asking a question, so if we're looking at things like properties of data types, at some point we might want to look at properties of data types that are mutually recursive. And these would tend to be, mutually inductive, right?
Mm-hmm.
So did you try anything like that? Is there any support for, I suppose that would be more related to the Isabel or vampire setup rather than QuickSpec per se, but I suppose for Isabel interaction that would be at some point useful.
Yeah, I mean, so what it does now in for instance in Isabel is that it this hipster that I showed in the video, that's parameterized by some automated tactics that I've written, and there you could plug in other automated tactics that perhaps handle mutual recursion better than here. I was just telling it that it could do. I think it was allowed to do structural induction on the data type, or it could do induction over the recursive structure of the functions.
Right.
But you can give it arbitrary tactics to use there.
So my, like what I would think is that this would mean that some of the candidate lemmas that you generate would be mutually dependent, right? And so you would want to prove them together, yes, and you'd have to, somehow automatically discover these are the ones that should be proved together, right?
Yeah, that wouldn't work today.
Okay.
But you would in principle, I guess in principle it would work, but it would need some engineering work to implement a tactic that can pair them up and do that in Isabel, and getting these proof contexts right, which will probably be a non-trivial engineering task. So that's nothing that we're planning on implementing but right now, but it would certainly be possible in principle. If that answers, I hope that answers your question.
Yeah, sure.
Cool. Any last questions from either in the room or online? Okay, I guess we should thank Moa again.
Yeah.
Thank you very much for coming.
Thank you.
Thanks, Moa. I
super interesting.
will email additionally.
Yes, yes. I know you had some interesting new projects too.
Yeah. Okay. Yeah. I will come again.
Yes, yeah. I'm curious to hear about it, and I'm sure maybe Solern and Nick, who are working on this as well, will be interested.
Thanks.
Bye for now.
Thanks, Moa.
Bye.
Bye.